In this video, I want to take a look at the algebra of complex numbers. Now, you probably got exposed to complex numbers in an intermediate algebra class or pre-calculus class or something like that, but we really don't use them at all in calculus. It's here in differential equations where we first start to use complex numbers more extensively, and so I'm going to spend a little bit of time helping you, showing you some of the algebra that you probably haven't seen before. So here we go. Remember, we did see this a little earlier this quarter, that e to the I theta is cos theta plus I sine theta. This is called Euler's formula. Essentially, it's the polar coordinate version of complex numbers, where theta is the angle measured from the positive x or the positive real axis up to wherever your complex number is. And we can see that this works with some of the numbers that we're familiar with. For instance, the number 1 I claim is e to the I0, right? In the 1 is 1 out in the positive x direction, in the positive real direction, and so the angle from the positive real direction is 0. But notice cos 0 is 1 and sine 0 is 0, so this is 1 plus 0i, which would just be 1. 1 is equal to 1, sure. Okay, I'm going to represent it this way as e to the I. 0. Likewise, 1 could be written as e to the I 2 pi, because 2 pi would say go all the way around once. Well, you've gotten yourself back to 1, but back to the real axis there, so a distance 1 away is the number 1. And look at that, it works. Cosine of 2 pi is 1, sine of 2 pi is 0, so again this is 1 plus 0, which is 1. Good. There's infinitely many ways we could do this, because we could say e to the I 4 pi or e to the I 6 pi or e to the I any even integer times pi would be equal to 1. Likewise, we could do a similar thing for minus 1. Now minus 1 is over on the negative x-axis, right? So x-axis, I keep saying x, it should be the real axis, because we got the real axis and the imaginary axis. So if you're going over there, it takes an angle of pi to get over there. So minus 1 is e to the I pi. Which, by the way, notice if you took the log of both sides here, you'd have the natural log of minus 1 is equal to I times pi. Yeah. Although, interestingly, negative 1, the natural log of negative 1 might also equal I times 3 pi. Let's not get into natural logs. Natural logs are definitely related here, but you can see that they're going to be multi-valued, that you've got to take a principal natural log and then you have all these other natural logs as well. But anyway, e to the I pi, I could rewrite as cos pi plus I sine pi. And notice that the cosine of pi is minus 1 and the sine of pi is 0. So again, this is minus 1 plus 0, and sure enough, that's equal to minus 1. Likewise with a 3 pi in there, or 5 pi, or 7 pi, or any odd pi would get you to minus 1. On the other hand, take a look at I. I is 1 up on the imaginary direction, and to get there from the real direction, positive real to positive imaginary, is an angle of pi over 2. So this is e to the I pi over 2, which I can double check. Cosine pi over 2 plus I sine pi over 2. Now the cosine is equal to 0 at pi over 2, and the sine is equal to 1. So this is 0 plus 1i, which is just I, sure enough. And likewise, we could do 5 pi over 2, because 5 pi over 2 would be, go all the way around once, that would be 4 pi over 2's, and then one more would get you up on the real axis again. Not the real axis, the imaginary axis, and you're up there at 1. And so e to the I 5 pi over 2 would be cos 5 pi over 2 plus I sine 5 pi over 2. Cosine 5 pi over 2 is 0, sine 5 pi over 2 is 1. So sure enough, this is equal to I, right? And we could do this with, what would be 9 pi over 2, or 13 pi over 2, or 4n plus 1 pi over 2, right? Anyway, lots of different ways that you can represent that number I. Here's another one that's not quite as obvious, but 1 plus I. So from the origin, you move 1 in the real direction and 1 in the imaginary direction. So you're looking at that diagonal off into the first quadrant. So the angle would be pi over 4. The distance away from the origin there isn't just 1 anymore, it's square root of 2, because the real component was 1 and the imaginary component was 1, so the diagonal is radical 2. So I would call 1 plus I radical 2 times e to the I pi over 4. And of course you can double check. The e to the I pi over 4 is cos pi over 4 plus I sine pi over 4. Cosine of pi over 4 is 1 over the square root of 2. When you distribute that in, 1 over the square root of 2 times square root of 2 is 1. Likewise, the sine of pi over 4 is also 1 over the square root of 2, which when you multiply by radical 2 gives you 1. So this would be 1 plus 1i, which is what we said it was over here. Okay. So this way of representing complex numbers as exponentials, it turns out is going to be really nice for us, particularly when we're trying to raise something to a power or find a root, a square root or a cube root or something like that. Okay, so that's what I want to talk about next, finding powers and roots of complex numbers. Okay, now let's recall from a previous video when we first started talking about complex numbers, the geometry of complex numbers, for instance, that when you multiply two together, that what's happening is you're multiplying the two radii together and you're adding the two angles together. Okay? Not at all obvious when you deal with complex numbers in their real and imaginary components. A plus bi times c plus di is, what is it? It's ac minus bd is the real component, and bc plus ad is the imaginary component. Anyway, it's not at all obvious that what you've done is multiplied the lengths and added the angles. But when you do it in polar form, it is immediately obvious that it works. Okay. So rather than, when I'm trying to raise something to a power, rather than writing it a plus bi to the n, I'd rather write it in polar form to the n, because then it's very easy to see what happens. Raising a product to the nth power raises each of the two things to the nth power. So you got r to the n, and then you got this exponential to the n. But when you have an exponential that you have something to a power, what happens is the two powers multiply together. Essentially, you're adding e to the I theta to itself, or you're adding the I theta to itself n times, and what you get is I times n theta. So raising a number to a power raises the radius to that power, and it multiplies the angle by that power. So if you're raising it to the third power, you're going to multiply your angle by 3. If you're raising it to the seventh power, you're going to multiply your angle by 7. Right. So here's a couple of examples. That's raising to a power. Taking a root. Taking a root like a 7th root or an 8th root or a square root or whatever, that's just raising to a fraction power, right? So when you're taking the nth root, you're raising to the 1 over n power. And so what happens here, like we have right here, the radius gets raised to that 1 over nth power, and the angle gets divided by n. The exponential gets raised to the 1 over n, so they multiply the exponents together. So multiplying by that 1 over n ends up dividing the angle by n. So a couple of examples. Square root of 1. I mean, we all know the square root of 1 is 1 and has another square root that's over there minus 1. But look at how we can get that by using the notion of this polar form of the complex number. So I can write the number 1 as e to the I0. Right? When I raise that to the half power to take the square root, then I'm just cutting that angle of 0 in half. Well, half of 0 is still 0, and it looks like e to the I0, which is still 1. It's hardly worth all that effort. But maybe this is worth the effort here, because I can also write 1 as e to the I2 pi. Now when I cut that in half, I cut that exponent in half, right, because I'm raising the whole thing to the half power. So the exponent gets cut in half, and so I get e to the I pi as my exponent here, the I pi. Well, e to the I pi is over there on the negative axis. It's minus 1. So I can generate both square roots of 1 by just writing 1 in two different forms of the exponential version of the complex number. Right? Now you might say, well, what you could do e to the I 4 pi. You're right, I could. And when I raise that to the half power, I'd take the 4 pi divided by 2, so that would be 2 pi. I get e to the I 2 pi. Well, that's where positive x-axis is there. That's all the way back around to 1 again. So using a 4 pi here would get me back to the answer of 1. Using a 6 pi dividing by 2 would be 3 pi, which would get me back to the -1, and so on. So yeah, there's infinitely many ways of writing 1, but when I raise that to the half power, I'm only going to get one or the other of those square roots. Likewise, I could look at the cubed roots of 1. And so I'm going to do e to the I0, or e to the I 2 pi, or e to the I 4 pi. Those are all different ways of representing the number 1. And then I'm going to raise them to the 1/3 power to take the cubed root. So this one, I still get an e to the I0, which is 1. Yes, 1 is its own square cubed root. Here I got e to the I 2 pi over 3. Well, 2 pi over 3 is, where is that? That's out in the second quadrant. So I've got cos 2 pi over 3, I sine 2 pi over 3. So it's got a negative real component of -1/2 and a positive imaginary component of square root of 3 over 2. And likewise, if I use e to the I 4 pi to represent the number 1, then you raise that to the 1/3 power. It divides the angle by 3, and I got 4/3 for my angle now, which puts me down into the fourth quadrant, because 4 pi, 1, 2, 3, 4, 4 pi over 3, sorry, is in the third quadrant, at -1 over square root of 2 for the real part, no, -1 over 2 for the real part, and minus radical 3 over 2 for the imaginary part. I want to just take a quick look at plotting those three. There's the 3 cubed roots of -1, no, sorry, of +1, 3 cubed roots of +1. So there's 1 and -1/2 plus radical 3 over 2 and -1/2 minus radical 3 over 2. Interestingly, those 3 cubed roots of -1 are on the corners of an equilateral triangle, but the distances here are all the same. That would be an equilateral triangle. How about fourth roots? Fourth roots of 1. 4 different ways of writing 1 as e to the I times some even number times I. Raising that to the 1/4 power to take the fourth root. I get 1, 2, 3, 4 different things here, and apparently there's a parentheses here that doesn't need to be there. But what I get are 1i minus 1 and minus I are the 4 fourth roots of 1. Taking a look at those on the graph, you can see they actually are on the axes there, and they would actually be the coordinate, the corners of a square. You might imagine that if you tried to take the fifth root of 1, you would get this 1 here, and you'd get 1, 2, 3, 4 others that would be on the corners of a regular pentagon, and that is exactly what happens. One thing to notice is that the roots here are always real, or they come in complex conjugate pairs. Right? This is related to what we talked about in the last video of polynomials factoring into linears and quadratics. But we will see more of that later. Okay, -1, square roots of -1, cubed roots of -1, same process. Cubed roots of -1, notice there's -1 plus 1/2 minus radical 3 over 2 plus 1/2 plus radical 3 over 2. Those come out from just writing that -1 as an e to the I something, in this case an odd number times pi, raising it to the 1/3 power. So cutting the angles by, dividing the angles by 3, and then interpreting that using Euler's formula. Fourth roots of -1. Fourth roots of -1 is interesting to me in that there aren't any real fourth roots of -1, right? When I look at what they are, And I'm going to calculate them in the same way, e to the I 1 pi, e to the I 3 pi, e to the I 5 pi, e to the I 7 pi, all different ways of representing the number 1, and then raise that to the 1/4 power, which is dividing the angle by 4, and I get these 4 points. 1 over radical 2 plus 1 over radical 2i, and minus 1 over radical 2 plus 1 over radical 2i, minus 1 over 2, sorry, minus 1 over radical 2. Everything's just 1 over radical 2. X and y coordinates are 1 over radical 2 plus or minus. And those are all the fourth roots of minus 1. Notice, for instance, this one. The angle here is pi over 4. And so if you multiply that angle by 4, it would get you 1, 2, 3, 4. It would get you out to pi. Pi over 4 times 4 is pi. And that would get you out to minus 1. So if you raise this number to the 4th power, it'll get you to minus 1, which means it is a fourth root of minus 1. Likewise, this one over here with an angle of 3 pi over 4, if you do 3 pi over 4 4 times, that would give you 3 pi. Well, 3 pi is all the way around once and another pi, which is getting you back to minus 1. Okay. So those are the 4 roots of minus 1. And lastly, I want to just take a look at, you can even take square roots of complex numbers. So for instance, what's the square root of I? Well, I is e to the I pi, or e to the I 5 pi, or e to the I 9 pi. There's lots of ways you could do this, but raising it to the half power to take the square root cuts the angle in half. So now I'm looking at I pi over 4s and I 5 pi over 4, and that's actually in the first quadrant. Angle pi over 4, right, is up in the first quadrant. So 1 over radical 2 plus 1 over radical 2i, and 5 pi over 4 would be down in the third quadrant, and then you'd end up at minus 1 over radical 2 minus 1 over radical 2i. These actually are two of the answers that were up here, which makes some sense to me because since I is the square root of minus 1, that if I take the square root of the square root, I should be getting a fourth root. So the square roots of I are actually 2 of the 4 square roots, sorry, 2 of the 4 fourth roots of minus 1. Okay. Anyway, we will be using this stuff to help us solve some differential equations here in the next video.